Hmm?
You usually miss.
Oh, I do. There we go. Are you all comfy? Oh, that's cool. I said that's a cold board. I leaned back and. See all your students coming? Are they your students? Huh? Are they your students? They are. Yeah, I know. I know.
Can I try to pet her again?
Hold on,
I actually meant to bring a dog treat with me.
hold on. Let me grab her. Come say hello. Come say hello. Yeah.
They didn't send me the shirt.
Okay, so so it said
Yeah, no.
At least my day on Monday, so. So, when they Did she say? I do small.
Good girl. It's that time of the morning. Okay. So we're gonna pick up where we left off on Tuesday. We started a discussion of alcohols. What we're gonna get into first is we're going to get into the naming of alcohols. Then we're gonna talk about the properties of alcohols and the reactions of alcohols. If time permits, then we'll have a brief discussion related to phenols. And then we'll talk about the acidity of alcohols and phenols compared to alkanes and stuff of that nature. So we'll just have to see what time we have available to us. Because I don't want to rush alcohols, because alcohols is a precursor to several compounds containing oxygen. And so I don't want to really rush alcohols so that you get that introduction to these compounds. So the first thing we got to deal with is the naming of alcohols. The goals when we're talking about the naming of alcohols is first we're going to learn to write the systematic names for simple alcohols. Then and also learn to draw the structure given its name. With the structure, most of the time I'm going to be using condensed structures, though you should be prepared to use line structures as well. We're going to learn to classify alcohols as a primary, secondary, or tertiary alcohol. And then we're going to define what is a glycol, which is going to be a very small, the definition of glycol can be extremely large, but with respect to the compounds that we'll refer to as glycols, it is going to be a very small subset. So systematic names, the process, folks, is the same. You name the parent, you come up with a numbering system, and then you put it all together. The process is going to be the same no matter what type of organic compound we're talking about. It's just the process differs slightly in who is part of the parent compound. So back when we talked about alkanes, it was simply the longest chain. And then we got into alkenes, and it was the longest chain that had the double bond. Now we get into alcohols, and it's going to be the longest chain that has the OH group. So the process is still the same. And we're going to replace the ending E, whether it's in the alkane or the alkene or whatever, we're going to replace the ending E with the ending OL. So let's just begin with this, just with a parent compound. Here we have, again, we're going to choose the parent compound based off of the longest chain that contains the OH. Well, the OH group is attached to the entire chain here. So as far as the parent is concerned, there's 1, 2, 3, 4, 5 carbons. So 5 is pentane. So this would be a pentanol. Basically, we replace the E with an OL. With cyclic groups, it's the same process as before. The cyclic group has to contain the OH. Whoops, wrong thing. And so when we name this, the cyclic group is cyclopentane. So this would be cyclopentanol, because we replaced the E with an OL. So again, the process for finding the parent is the same as what we've already been doing. The naming of the parent is the same as what we've already been doing, except we replace the ending E with an OL group, with an OL to indicate that it's an alcohol. Now, numbering. You're going to number the carbon atoms so that the OH group is assigned the lowest number possible. This was a lot like what we were doing with the alkenes. So in this one, with our numbering system, if we're going to number it so it has the lowest, the alcohol has the lowest possible number, then we're going to have to start from the right-hand side and number it from right to left, finding the longest chain. So in other words, our alcohol is on carbon 2 in this case. Because we wanted the alcohol to be as low as possible. Now, it's with a cyclic alcohol, it's the same as it was with an cyclic alkene. In a cyclic alkene, the double bond had to be the lowest numbers possible, 1 and 2. In a cyclic alcohol, the alcohol has to be the lowest number possible. So this one is going to be assigned number 1 that has the alcohol group. Get my pens to work today. And then our other substituent is going to be the next lowest number possible. Finally, we're going to write the name, placing the number that locates the alcohol prior to the parent. Now, again, it's not necessary if we've got monoalcohol or monocyclic alcohols, because the alcohol has to be on number 1. But for everybody else, you would have to give a number. So let's just look at some. So we had carbon 1, 2, 3, 4, 5, 6. This would be 5-methyl 2-hexanol. The parent was hexane because that was the longest chain containing the alcohol. The alcohol had to have the lowest number possible, so we labeled the chain from right to left. And then when we named it, we labeled the substituents, just like we've been labeling the substituents. And we said where the alcohol was located, just like what we would do with an alkene. So folks, you're treating these alcohols a lot like you treated the alkenes, which you've already had experience with. This next one, we would find the longest chain, and we would number the carbons so that the alcohol has the lowest number possible. Then we would name this compound, and this would be 1-butanol. If I go too fast because I've already written so much of this, let me know, folks. I'm trying to take my time, but I know I speed up a little bit. Why don't you name the next one in line? You should have come up with 4-chloro, 6-methyl, 2-heptanol.
So.
Go ahead and try to name the next one as well. that one would have been 2-methylcyclohexanol. Again, I didn't label the number for the alcohol because when you're talking about a a cyclic compound that only has one alcohol, it's always number 1. So you don't have to label it. Questions? Yes.
Is it considered incorrect if you, like if you did put 2-methyl-1 cyclohexanol?
Technically, it's not incorrect.
I would just prefer to just do the cyclohexanol. Oh,
It's common to just leave off the number.
okay.
Is that just for the cyclos? Or is
That
for
is
all?
just for the cyclics. For everybody else, if it's not cyclic, you've got to label it. And the only reason it works is in a cyclic compound, the alcohol always has to be number 1. Okay, so and second point we were supposed to discuss is what's called a diol and a glycol. Folks, a diol simply just means that there's 2 hydroxy groups attached. There's 2 OHs attached to it. Just like we would say dichloromethane or dimethyl, you got to say that there are 2 alcohols. So it becomes a diol rather than just an ol on the end. This is the same as when we were dealing with alkenes and you had 2 double bonds, you had to call it a diene. Now, if you have 2 alcohols, you call it a diol. When you're doing the numbering, you want your alcohols to have the lowest numbers possible. And now and you've got to number them, just like when we were talking about an alkene where there were 2 double bonds, you had to number the carbons where those double bonds were. If you got a diol, you got to number the carbons where the 2 alcohols are. So here's an example. We're going to start by numbering the carbons so that they have the lowest number, the alcohols have the lowest number possible. So 1, 2, 3, 4 would give us the alcohols with the lowest numbers possible. Since the alcohols are our only substituents on here, we're ready to do this and we just have to give the number for the 2 alcohols. So it's 1, 3 butadiol. Or you can, if you're being exact, the way they describe it, you can say butane diol or butadiol, butane diol. But you'll see it most often written as 1,3 3 butadiol.
Which would you prefer?
For active purposes, probably the first one. I just want you to be aware that if you hear butadiol, it's butanediol. They're the same things. Ethadiol is ethanediol. Hexadiol is hexanediol. Let's look at the next one. You number your carbons so that they're the lowest number possible, which is a 1, 2. So this would be a 1, 2 ethane diol. Folks, if you read these things, it makes sense. Ethane means it's a 2-carbon chain. Diol means that there's 2 alcohol groups. And the 1, 2 is telling you where the alcohols belong. The next one. Number your carbons so that they're the lowest numbers possible. So 1, 2, and 3. So this would be a 1, 2 propane diol. Why don't you try the next one? That one would have been 5-methyl 2,4-hexane diol. Yes.
Is there any instance where the methyl group would get the lowest number?
No. The substituents like methyl, ethyl, isopropyl, butyl, those will never be your lowest number. The functional groups are more important than those types of substituents.
Okay.
So that's going to be true for everything that we do. The functional group will be the most important factor.
So if there were 7 of those, we would still number it the way that it's numbered.
Correct. Because the alcohols are the most important things. One more. This one would have been 2-methyl, 1,2-propanediol. Any questions? Okay, so the start of this was diols and glycols. What is a glycol? Folks, glycols are just simply special diols. Glycols are simply special diols. They're specifically diols where the OH groups are on adjacent carbons. We've actually seen a couple of these glycols. Now, technically, you could name any compound that has the OH groups on side-by-side carbons as a glycol. But there are two that their common name is used more frequently than their IUPAC name. And these are the first two glycols. Previously, we named this one 1,2-ethane diol. This is the IUPAC name. But you will also see this compound listed as ethylene glycol. In fact, you'll see it listed as ethylene glycol before you'll see it listed as 1,2-ethane diol. So the difference is common name compared to IUPAC name. But this is one case where if I were to go find a bottle of it upstairs, I would be looking for ethylene glycol, not the name with the diol. We named the second one 1,2-propanediol earlier. Again, that is its IUPAC name. But it is more commonly known as propylene glycol. So we know 1,2-ethane-diol and 1,2-propane-diol were glycols. Of the other three compounds that we did at the previously, which of those three compounds could be called a glycol as well? Of the previous 5 diols, we know that ethane-diol and propane-diol were glycols. What other one was a glycol? Remember, to be a glycol, the alcohols have to be on adjacent carbons. The last one, that's the only other one that could be called a glycol because it's on adjacent carbons. That's what makes it a glycol, is the alcohols have to be on side-by-side carbons. Questions?
So would that one be 2-methyl propylene glycol?
That one would be, technically, no, it's isobutyl glycol, isobutylene glycol, because it could also be the isobutyl group.
Gotcha.
So be prepared to recognize a glycol, but as far as knowing how to name glycols, it's only going to be the first two, ethylene and propylene. I'll keep that simple.
So, which mean they will always have the imine glycol? Propylene.
Yes, they're always the common names are always the ylene glycol, YLENE glycol. Okay, the last thing we were supposed to do is learn how to classify alcohols as primary, secondary, and tertiary. And folks, if you go back to chapter 12, where we learned primary, secondary, tertiary, and quaternary carbons, you will see that the same rule applies for alcohols. A primary alcohol is going to reside on a carbon that has only one other that has 2 hydrogens and a carbon chain. A primary alcohol is going to reside on a carbon that has 2 hydrogens and an alcohol chain. Alkane chain. A secondary alcohol is going to reside on a carbon that has only one hydrogen and two alkane chains? A tertiary alcohol is going to reside on a carbon that has no hydrogens and has three alkane chains. Notice that the degree, and I haven't shown you the tertiary yet because I'm giving you time to write. But notice that the degree, the classification, is related to how many alkane chains are attached to the carbon with the alcohol. If it's first degree, there's one alkane chain attached to the carbon with the alcohol. If it's second degree, there are two alkane chains attached to the alcohol, the carbon with the alcohol. So the degree is telling you how many alkane chains is attached to the carbon with the alcohol. Yes.
So the R's are the alkane chains?
Yes.
Why is it like R?
R is just a generic, it's just generic for, and I can't tell you why they chose R other than there is no element that is just plain R. So there's no way of confusing it with something else. But why they chose R in particular, I don't have the answer. I'll have to look that one up. Now, you'll notice that on the secondary and on the tertiary, I use R prime. I use R prime and R double prime. All that means is that the alkane chains can be different. You can have a methyl and a ethyl group. It just means that the alkane chains can be different. That's why the primes. Any questions about recognizing a primary alcohol, a secondary alcohol, and a tertiary alcohol? If you can't do that, then when we get to the reactions, it's going to be a challenge. Because when we get to specifically when we get to the oxidation reactions, primary alcohols will undergo oxidation and secondary alcohols will undergo oxidation, but tertiary alcohols do not. So you need to be able to recognize the type of alcohol. Okay. So now we're going to move on to the properties of alcohols. And we've actually already started this discussion early on. We discussed the fact that the alcohol portion of the compound looks kind of like water. Therefore, it can hydrogen bond and do other types of reactions similar to what water can do. But there are limitations. The OH end is considered to be a hydrophilic end of the compound. Hydrophilic meaning that it likes water. The R group or groups tend to be hydrophobic. Meaning that they dislike water. Now, a alcohol's behavior, its property, is really dependent upon which end is the most important. The property is dependent upon which end of it is the most important. Is the hydrophobic end the more important end, or is the hydrophilic end the more important end of the molecule? And that is all dependent upon the length of the R. The rest of the chain. If the R group, the hydrophobic group, is between 0 carbons, meaning it's not a carbon, it's a hydrogen, to 2 carbons in length, then the hydrophilic end is more important.
See that one more time.
If the hydrophobic end, the R group, is 0 carbons in length, meaning it's actually a hydrogen, to 2 carbons in length, then the hydrophilic end is actually more important. And if the hydrophilic end is more important, then it behaves similar to what water would. So it would be soluble in water, and it can dissolve ionic compounds. So ethanol can dissolve ionic compounds. Propanol can dissolve ionic compounds. Now, when your R value becomes greater than 2 carbons, the alcohol is no longer going to be soluble in water because the hydrophobic end becomes more important. So basically what we're getting at here, folks, is if I take methanol, ethanol, or propanol, the OH group, because of the size of this these compounds, the OH is more important. But when I get to butanol, or pentanol, and I continue, the alkane chain becomes longer and longer. And therefore the R group is more important. Again, this importance determines whether it is hydrophilic, meaning it's going to be like water, it's going to behave like water, stuff like that, or whether it's hydrophobic, which means it hates water and therefore doesn't behave like water. Now, if you have a diol or a triol, or continue, meaning you have multiple alcohol groups, increasing the number of alcohol groups increases hydrogen bonding capabilities. And an increase in hydrogen bonding capabilities increases the likelihood that it'll dissolve in water. One example is glucose. Glucose is a 6-carbon chain. If you're simply looking at the number of carbons, then you would think, well, that's hydrophobic. But we know that glucose, sugar, dissolves in water. That is because sugar has multiple alcohol functional groups. And so we increase the number of alcohols, we're going to increase its solubility in water. Questions? Now, as far as melting point and boiling point, just like with alkanes, when you increase that R, you increase the melting point and boiling point. You increase the lengths of R, you're going to increase the melting point and boiling point of an alcohol as well. The reason you'll increase the melting point and boiling point of an alcohol has to do with the fact that, yes, you have hydrogen bonding on that hydrophilic head. But when you start to increase that R chain, you're increasing the London dispersion forces that are available. And as you increase the London dispersion forces available, then you're going to increase the melting point and boiling point. So kind of to summarize the general rule, if your carbon to oxygen ratio is 1 to 1 or 3 to 1, all the way up to 3 to 1, 1 carbon to 1 oxygen or 3 carbons to 1 oxygen is going to be soluble in water. If your carbon to oxygen ratio is 5 carbons to 1 oxygen or greater, then it's going to be insoluble in water. The other piece is you increase the melting point and boiling point with increases in number of carbons and increasing number of oxygens. Questions about the properties of alcohol? Then we're going to get into the reactions of alcohols. And we're going to talk about 2 specific ones. We're going to talk about dehydration. And we're going to talk about oxidation. If you become dehydrated, what happens? What does it mean to your physical being if you become dehydrated? Lack of water. Dehydration is a reaction that removes water to make a double bond. Now, a mixture of alkenes can occur when more than one type of dehydration, when you have more than one option for the dehydration. In this particular case, the major product will be the alkene with the greatest number of alkyl groups directly attached to the double bond. Now, the way the double bond is made is by removing an OH group from one carbon and a hydrogen off an adjacent carbon. So let's look at an example or two. Let's take the compound of 2-butanol. We're going to remove the OH from group off of an carbon. So we're removing the OH. We're then going to take a hydrogen off of an adjacent carbon. Well, in this case, we have two possibilities that where we can remove the hydrogen. So that means we can form 2 double bonds. Let's just look at this a little bit more spread out. One option is that I could remove that OH and that hydrogen. And if I do so, then I'm going to get CH3, CH, double bond, CH, CH3. The other option was to take CH3, CH2, COH, H, CH3, And I can remove these two. And if I do so, then I get CH3, CH2, whoops, CH double bond CH2. The first of these is the major product, and the second is the minor product. This comes back to that statement I made about the major product will be the alkene with the greatest number of alkyl groups directly attached to the double bond. This one had one alkyl group on the left, and it had one alkyl group on the right. Whereas in this particular case, you only had one alkyl group on the left. So since the top one had an alkyl group on both sides of the double bond, it was the preferable one. Now I should make one more comment about this. Well, I have to make one more comment, and that is the dehydration only occurs in the presence of an acid catalyst. Specifically, an H2SO4 catalyst, which is the strongest of acid catalysts. So to write this, I would actually need to include H2SO4 catalyst on the reaction arrow. Let's look at another example. Which alcohol or alcohols yield 4-methyl 2-hexene on dehydration? And are there any other alkenes that can arise? From the dehydration. Okay, first things first, let's get 4-methyl 2-hexene in place. CH3, CH, well, let's do it this way first. Let me get in the carbons. I have 2-hexene and I have 4-methyl. That is my starting compound. I mean, excuse me, that is the ending compound. So where did it come from? Well, one option that it could come from is we could have had CH3, CH2, CH, CH3, CHOH, CHH, CH3. The other option that it could have come from is CH3, CH2, CH, CH3, CH, H, CH, OH, CH3. First of all, I'm gonna let you catch up to me and I want you to look at it and see if that makes sense, what I did to get to this point. Any questions about how I got to this point? So all I did was back up and said, if I did a dehydration, that means I had to start with an OH and an H on the two sides of the double bond. So those are the ones that I drew out so that you could see the OH and the H. So these are the two alcohols that could have yielded 4-methyl-2-hexene on dehydration, but one of them is going to be preferred. Now, to know which one is preferred, you got to figure out what the other product could have been. What is another product that I could have gotten out of the first one here? What is another dehydration I could have done? What is another alkene I could have gotten?
Double bond could have been in between, could be this way instead of that way.
The double bond could have been CH3, CH2, C, CH3, double bond, CH, CH2, CH3. Yes, that's one of them. Or that's the other one. Now, out of these two, which would have been the major product? The top or the bottom? It would be the bottom. Why? Technically, there is an alkyl group here, an alkyl group here, and an alkyl group here. So there were 3 alkyl groups there compared to up here where there was just an alkyl group on the left and an alkyl group on the right. So in this configuration, that was a minor product. What would have been the other product that could have come from the second one I drew? The other product would have been CH3, CH2, CH, CH3, CH2, CH, double bond CH2. I'll just give it to you because we're running out of time. That would have been the other option, is to take, instead of the hydrogen that I took, I could have taken a hydrogen from the CH3 group. Because it's an adjacent carbon. Now, which of these is the major product? The top or the bottom? In this particular case, this one is the major product, and this one is the minor product. Because there's only one alkyl group here. So if this reaction were to occur, we would rather start with this compound if we're wanting this as the major product. If we want 4-methyl-2-hexene as the major product, we would start with the second alkyl group, or second alcohol I drew. Questions? We will pick up with another example of this on Tuesday, and then we'll get into the oxidation of alcohols, which is actually easier than the dehydration. So in other words, today's active is going to be about naming alcohols and the properties of alcohols. I will save the reactions of alcohols for another time. For Tuesday, if you will read 14.4. Through, go ahead and read through 14.10. I don't know if I'll get to all of that, but on Monday I'm supposed to lecture in lab. And so that will be what I'll be focused on, is finishing up 14 in the lab on Monday. Any questions? If not, I will see you on Monday.